So we have different types of, well, I'm not going to say continuity, discontinuities that we can have for our functions as far as like determining if they're like continuous or not. Which this will like be a continuous thing that we're seeing throughout the year of like dealing with when things are continuous or not. And things can be continuous like at an endpoint, but not necessarily like at one endpoint, but like not necessarily the other. But discontinuity, we have removable, which is if there's like a hole. There's a jump discontinuity, which is where kind of what you would see with like a, what is it called? I'm going to say a step equation. But anyways, piecewise, that's what. And then there's infinite discontinuity where it like goes off to like an asymptote. And then there's, well, those are the main ones that we use, I think. There's also an oscillating discontinuity, but we don't really, that's like with a trig function, and we don't really see those that often. That's like if there's like a gap in a trig function, basically. So the first one say to find the points of continuity and the points of discontinuity of the function, and then identify each type. So basically, you're going to have discontinuity if you have like pretty much anywhere you'd have an asymptote, you're going to have a discontinuity. So like if you have a fraction equation, you'll have them. If you have trig functions, anywhere they have an asymptote, like cotangent, tangent, those things would have one. So yeah, anyways. So we'll just look at some examples to see it. 2, y equals x plus 1 over x squared minus 4x plus 3. So to determine if they have a discontinuity in like the type, we're going to look at with one like this, when we set the denominator equal to 0 and solve. So anywhere that it's undefined, I guess would be a better way to say it. So I would need to factor this. What would the denominator factor into?
X minus 1, or, yeah, x minus 1 and x minus 3.
Yeah, x minus 1 and x minus 3. Set those equal to 0. So that means at x equals 1 and at x equals 3, we have a point of discontinuity because that's going to cause a problem in the equation. And these, because obviously it's a vertical asymptote there, it's going to be an infinite discontinuity. Four, y equals the absolute value of x minus 1. So some of these just, you kind of need to know like roughly what a graph looks like. So the absolute value graph is obviously like a V. So is there anywhere that like that graph doesn't exist, or that there's like any issue points in a thing, right? Yeah, it goes on to infinity. Obviously it doesn't cover all y values, but x values are what we're looking at. So it covers all the x values. So this one does not have any discontinuities. And so that's all that these ones are asking us for. 6. I've got y is equal to the cube root of 2x minus 1. Do you know what a cube root graph looks like?
Like this.
That's cubic. But take that and put it sideways.
Okay.
So basically a cube root graph looks something like this. So it's like the square root part of the graph would be up here, and then it continues down this way. So there's nowhere that this doesn't exist, or like that there's a problem or anything like that. No gaps or holes or places that it's jumping. So this one is also none. There's no discontinuities in that one. If I have y equals the cotangent of x. What do you know about like the cotangent graphs?
It does jump.
Yeah. It has like asymptotes and it's like keeping it between it. So cotangent, just for a little refresher here, would be basically from 0 to pi. We would have asymptotes at 0 and pi, and then the graph would essentially be coming down through here at pi over 2. So this one's a little bit, because it wants to know if there is a discontinuity where it is. So this one obviously has them. There's infinite discontinuity. Because it hits the asymptote and just like it doesn't cross it, it just keeps going in the direction. So what we would say as to where they are is that they are at x equals k times pi for all integers of k. Because any increment of pi that's an integer would be there. If you had like tangent, then we would say at like k times pi over 2, where k is like what is it, odd integers of pi over 2 or whatever. But it would be the same thing with that. And then you could also have them with secant and cosecant, but I have to draw them out to see where the thing so anyways, but just so you're familiar with those. 10, y equals the ln of x plus 1. So log graphs, let me see if I can put this up here. So if I typed in the ln of x plus 1, zoom 6. Let me do this compared to a regular log graph here. Just ln of x. A normal log graph starts at 0 and, or like, there's an asymptote at 0 and it goes basically up and over. This one is just shifted over. So the only place that this can be continuous is in its domain values. So only values from basically anything greater than -1 would be in its domain, right? Because that's what I was trying to show. The ln of 0 is undefined. You can't do anything with that. So anything greater than that would be in its domain of the graph. So it's discontinuous at all points not in its domain, because it's going down with the asymptote all the way down, so we can't technically account for all of that. But that's how we would say it. Discontinuous at all points not in its domain. Okay. So if we wanted to show this mathematically, basically x plus 1 to whatever's in here has to be greater than or equal to 0. Well, actually, it can't be equal to 0. It has to be greater than 0. So x is greater than -1. It's continuous here at all points here. So anywhere outside of that is, which isn't in the domain to begin with, would be where it's discontinuous. Because we haven't seen a jump discontinuity yet, I want to look at one of those, so it's an odd one, but number 7, y equals the absolute value of x over x. So this one, you wouldn't necessarily be able to just like probably visualize that graph. I mean, you could probably get to where you're plotting points and do it, but if we type it into y equals
Type in absolute value?
So let me see. Math. Where is it? Number. Oh. So when you click the math button, arrow 1 to the right to number, or NUM, and then it's the first option, ABS. So the absolute value of x divided by x. And then if we graph it, what you'll see is it starts down here, then it takes a little break, and then it jumps up here and it keeps going. And if you think about it, if you plug a negative value in, right, you're going to end up with negative values down here. But if you plug in positive values, everything's going to be positive. So, I mean, it kind of makes sense. But this one would have a jump discontinuity. At x equals 0, because that's where we see it go from being below to being above. So that 0 value, which is obviously where it changes from positive to negative. So if there's ever one that you're doing and you're not sure what the graph looks like, you're not completely sure, it's always good to look at it and see. But we can have ones like this where we need to evaluate, like, where's the domain, because it might be continuous on its domain, but it's not continuous elsewhere because there's an asymptote. So we're kind of like disregarding that part. Do you have your book? Because number 12 has like a picture, so I was going to try to, I may end up needing to do this differently, but basically 12 and then 14 and 16 all are part of the one picture. It's on page 84. So part A is, does f of 1 exist? B is, does the limit as x approaches 1 of f of x exist? C, the limit as x approaches 1 of f of x equal f of 1. And D, is f continuous at x equals 1. So these are different things that we'll have to answer with the picture that they've given to us. But I just like to have them written out so I can see what's going on. I'm going to see if I can put this up here for a second. I may have to just come over there. It might be easier. All right. So obviously you have your book in front of me, so you'll be able to see it a little bit better there, but just for tracking. So first thing we're looking, does f of 1 exist? So we're looking, is there a value for this function that when I plug in 1, I get a value? So basically f of 1 is 1, where that's where the blue circle is that's like actually filled in. So the answer to part A would be yes, and we normally would put the value it's equal to 1. They don't technically require you to put it, but now they want to know if the limit as x approaches 1 of f of x, does it exist? So is there a value, or like what is it approaching to know that does this limit exist? So if I'm looking from the left, What value is that?
0.
At 1?
Like from the left of 1.
So like 1's right here. So if I'm coming up this way, what value is this? Approximately. Obviously there's a gap, but if we just said from the left, what would you tell me that that's approaching?
2.
Yeah. And then from the right, what is that approaching?
2.
Yeah. So since they both go to the same spot, this one exists, and it's equal to 2. So yes, it's equal to 2. Now, C is where it gets a little bit more confusing. Or not confusing, but like, you have to really think about it. Does the limit as x approaches 1 of f of x equal f of 1? So if your first two things, which is why I put the numbers up there, or why like I write down what they're equal to, if they are not the same, then obviously that's not true. So 1 isn't equal to 2, so the answer is no. And then part D wants to know, is f continuous at x equals 1? If there's a hole and it's filled somewhere else, it's not continuous, so it would be no. And this type of discontinuity is removable because we basically have taken a value and we've put it somewhere else. So 14 then is, let me take this out and swap this back. At what values of x is f continuous? So we're looking at the graph and we're looking for where there is a continuity or like filled holes. So basically, it's continuous everywhere except for where the holes are. So like we've already established at x equals 1, there's a discontinuity that's removable. The other ones, like from at x equals 0, that's a jump discontinuity there because it is broken into that. And at 2 and 3, it would also be removable. So the way that we would answer 14 then is to say that, because it asks if it's continuous. So I would say continuous everywhere in the interval closed at -1 to 3 open, because that's where the circles are, except at x equals 0, 1, and 2. So obviously there's also a hole at 3, but we've accounted for that with the interval the way that we've written it as being an open interval. So then 16, what new value should be assigned to f of 1 to make the function continuous at x equals 1? What do you think? Basically f of 1 was 1, but the limit was 2. So what does it have to be to make it continuous?
2.
Yep. I just have to fill the hole. So x would need to be equal to 2. Or, let me, hold on, not 2. F of 1 would need to be equal to 2. There we go. Does that kind of make sense?
Yeah.
Okay. On all of that, I know it's hard to like kind of see it and look at it. All right. So 20, we've got these ones say find each point of discontinuity, that's part A, and then B, which of the discontinuities are removable, not removable, give reasons for your answers. So 20 is f of x equals this piecewise function, 3 minus x for x less than 2, 2 for x equal to 2, and then x less than 2. X divided by 2 for x greater than 2. So we want to know where the point of discontinuity is. So basically what I would do leading up to this is I would evaluate the two-sided limit of this graph. So if I were to kind of graph what this looks like here to the best of my ability, I need to go out a couple over here. I'm going to go up a couple over here. I'm going to essentially graph each piece of this piecewise function given the information that I have. So I'm going to start with when x is equal to 2, we know that it's 2. So I'm going to put a point there. Now, when x is less than 2, so that means anywhere on the left side over here of 2, I have 3 minus x. So what I would do is I would graph this like a normal equation of a line, basically. So I would have an intercept at 3, slope of -1, down 1, right 1, down 1, right 1. But I know that this is only greater than 2, so I'm going to put an open circle there. And then I'm going to connect this like that. Then over here, this is for x greater than 2. So say if I put in 3, it's at like 1.5. So I'd have a value there. At 4, it would be equal to 2. So something like that on that side. So almost looks like an absolute value, but not quite. So what I would recommend when we have a problem like this is kind of graph it out if you can. Some of them are more challenging to graph than others, just depending on the piecewise function. Like 21 is going to be a little harder to graph than, not that it's impossible to graph, but when I'm doing one like this that's piecewise, I would just plot points, except for like if it's an equation of a line. But 21 is 1 over x minus 1 and x cubed minus 2x plus 3. You probably don't know what those things just look like off the top of your head, so just picking a few points that meet the criteria are going to be your best bet on that. So now, before I actually answer part A, I would recommend that we find the limit as x approaches, since all of these deal with 2 from the left, and that's going to be of 3 minus x. I would find the limit as x approaches 2 from the right, which is going to be x over 2, or that would be the function that we're looking at. And then the two-sided limit as x approaches 2 of f of x. We'll see what happens. So as we approach 2 from the left, this side of it is getting closer and closer to 1. So this is going to be 1. As I approach 2 from the right, so coming from over here, that's also going to be 1. So that means then that my two-sided limit is equal to 1. Because if they're the same, then the two-sided limit is the same, and that means that the limit exists if the two-sided limit is the same value. So now I can look at find each point of discontinuity. Well, it's probably pretty obvious here because I've got an open circle and then I have a point there, that I have a point of discontinuity at f of 2 equals 2. And part of the reason that I know this is because the limit as x approaches 2 of f of x should be equal to f of 2 if it's continuous. So since the limit as x approaches 2 of f of x is equal to 1, but f of 2 is equal to 2, those are not equal, so that it is discontinuous at x equals 2. And then which of the discontinuities are removable or not removable. So obviously There's only one in this one. Some of them will have more than one. It just depends on the problem. Like if you look at 23 and 24 where they've given you the graph and you're doing these same questions but with the graph rather than the math, they obviously may have more discontinuities there that you're looking at. So B, this is a removable one. And they want us to give a reason. And so basically, essentially, I could point back to this being my reason right here. I already have shown it here for the reason behind that. But okay, what is next? Oh, these last couple are super easy. They're just mathematical. All right. Give a formula for the extended function that is continuous at the indicated point. So basically, 26, I've got f of x is equal to x cubed minus 1 over x squared minus 1. And they say that x is equal to 1. Well, if x is 1, what's the problem here? Well, 0 over 0, right, which is going to be a problem. So they want me to essentially find a way to rewrite this function so that it is continuous. Because right now it's not because of, well, predominantly the denominator, but obviously top and bottom are both 0, which is another whole level of a problem. So what I need to do is I need to see if I can factor the top and bottom and cancel something to rewrite my equation. So, do you remember the factoring for a cube? Okay, so it's the first term and the second term get written down first. So x, same sign, it's a SOAP formula. And then we take the first term and square it, so x squared, opposite sign, so plus first term times second term. So in this case, it'll just be x. And then the last one is always positive, and it's the last term squared, so that would be 1 there, like that. And then I think you know how to factor this one. What does that factor into?
X plus 1 and x minus 1.
Yep. X plus 1 and x minus 1. So then the x minus 1s can cancel. So then my new formula would be f of x is equal to x squared plus x plus 1 over x plus 1. And so if we put in 1 now, there's no issues. It's just going to work straight up. Now, that doesn't mean that it doesn't have a point of discontinuity elsewhere, but it's continuous at the point that they're giving me. Because this would have a point of discontinuity at -1, because that would obviously be a problem. But that's how we would rewrite that one. Let me see here. So 28 is kind of interesting. It's f of x is equal to the sine of 4x over x, and they tell us that x is equal to 0. So do you know, or well, obviously 0 causes a problem right now, right? Because if I put 0 in, the sine of 0 is 0, and then over 0, we obviously have a problem there. But is there any other value that this cannot be besides 0 that's going to cause a problem? On like a reasonable increment, obviously increments of 2 pi are going to cause a problem, or increments of pi are going to cause a problem on the top. But is anything going to cause the denominator to be 0 other than if it's 0?
A negative number? I don't know.
So as long as the denominator's not 0, we're good. So that's why I said this one's kind of weird. So this one's going to have to be turned into a piecewise function instead of us writing it a different way, like being able to cancel stuff. So this one is f of x is equal to the sine of 4x over x when x is not equal to 0. And then basically, if x is 0, then the function is equal to 4, which that's just, if you plug it in, you figure that out, essentially, the way it's going to end up working out. I wouldn't be too worried about that one. I just wanted to show you that that one's a little different. Most of them just cancel nicely, so you don't have to worry about it. That's just the one that's kind of weird. All right, the last one is using Theorem 7, which says, let me find it. Composite of continuous functions. So if f is continuous at c and g, if f is continuous at c and g is continuous at f of c, then the composite g of f is continuous at c. So basically, that's confusing in words, in which is how most of calculus is. In math terms, if I have f of x is equal to the sine of x squared plus 1, then what I can do is I can break this up into like two separate functions, and this is my composite function. So I'm breaking it into two separate functions to prove that if both individual functions are continuous, this is continuous. Now, we know what the sine graph roughly looks like, and we know that sine overall is a continuous function, right? It keeps on going. But I can prove that with this theorem. So if I let g of x be equal to the sine of x, well, we know that's continuous. And then if I have h of x, since they used f, I'm using h, be this inner part, so h of x is equal to x squared plus 1. Well, parabolas are continuous, right? So since that's also continuous, then I know that f of x is equal to g of h of x. That's my composite function. So by Theorem 7, g of, my gosh, what is happening? H of x is continuous. So if it asks you to use Theorem 7, it just wants you to break it down and then basically just show that each piece that you've broken it into is continuous. Most of them are not super complicated as far as how you would have to rewrite them. I think they're all pretty clear what they would need to be. So, a few problems to go with this stuff. 1, 3, 11, 13, 21, 23, 25, and 35. Obviously, don't necessarily have to do them right now or even this weekend, but just at some point soon-ish. I'm going to plan to start 2.4 on Monday. I would say we'll probably take 2 days on that section just because it's some stuff that's really important moving forward. So I would say maybe next Thursday quiz, but it might be Friday. It just depends on how it works out for sure with getting through it all. So just for pacing.